So yesterday we were doing some questions on oscillatory integrals, and today we'll continue from there itself. Okay, so we'll continue with the oscillatory integrals, and I was doing certain kind of integrals yesterday, and from there on, see here it is. Give me a minute. Okay. Okay. So yesterday we were doing some oscillatory integrals, as I told you, and today also we are going to move forward from here, from there only. Okay. So, okay, just give me a minute. Okay, this is it. Okay. So there were three kind of integrals that we have done till now. There were one that were trigonometric integrals. Okay. There were trigonometric integrals. Then there were some integrals of the form minus infinite to infinite, fx dx. Then there were some integrals which I would now call as some oscillatory integrals because they contained some cos mx and sin mx. And there were some miscellaneous integrals that I classified because there may be a possibility that your branch point or probably your singularity may lie on the contour itself. So there is a possibility. So those possibilities I'm covering under miscellaneous. Okay. Another thing that I want to know is that today, I want to tell is today or tomorrow, these are the last 2 days for this first phase of complex analysis. I'm not saying that we are at the finish of it because there are many subsidiary topics to it. For example, the topic like integral representations, where you may have you can derive like gamma functions and all sorts of functions, which are actually very useful in physics also. And secondly, the second phase of complex analysis, I will deal more with the physical situations. So for that, I need certain amount of um, understanding from your end also. That is like, for example, if I want to say that, okay, complex analysis is used in electrostatics. Okay. So in what ways or probably what are physical situations arise where you may have applications of complex analysis. For example, if I say quantum mechanics, so I would give you some situations. Obviously, we'll do it in the purview of mathematics only. We're not going to do much of physics there, but we'll try to understand how to cover that particular problem with whatever we have done till now. So that will go on, probably a lecture in a week or 2 lecture a week, it will go on. So, but the overall, we'll try to start more physics from next week onwards. Okay. Okay. So trigonometric integrals we have already done. So I will revise that particular. So things, for example, if you have some integrals of this sort, then what would you do? You would simply take sine theta and cosine theta as as e की power iota theta minus e की power minus iota theta upon 2 iota. You take cos theta is equal to e की power iota theta plus e की power minus iota theta upon 2. And you take e की power iota theta as z and you do all sort of things. So for example, when I say e की power iota theta is z, that itself implies that your mod z equal to 1, implies that you are on the unit circle. Okay. So such questions we have already done. Okay. Such questions we have already done. I'll just give you an example as to how you will be, so that it gets all over, so that you are able to understand what we were doing in till now. So for example, if I'm giving you a question, let's say this is your question, integration 0 to 2 pi 1 plus 2 cosine theta raised power n, and then you have cos n theta, you have division by 3 plus 2 cosine theta. What would you do about it? So how to go about these problems? So I already told you the scheme of things is to place cos theta as e raised to power iota theta plus e raised to power minus iota theta divided by 2. And you have to do e raised to power iota theta as z, and then you have to do this derivative in order to generate the differential term. So differential term d theta comes out as dz upon iota z. So this is your differential term. You can use it all over here. And you can see that as you are doing e की power iota theta is equal to z, it implies that e की power iota theta mod is mod z, and e की power iota theta का mod is 1. So you are on the unit circle, and the traversal is in the anti-clockwise direction. So the traversal is in the anti-clockwise direction. Okay. Okay. So traversal is in the anti-clockwise direction, and sorry. Okay, so this is a sort of integration. So your integration takes place on the unit circle. Okay, so this is how it is. So what you would do, you just replace cos theta as e की power iota theta plus e की power minus iota theta, and that would give you I think cos theta in terms of z. If you write, it will be z square plus 1 upon twice z, and just replace all over. So all over the place you can replace it. Further, what about this particular thing? So there is another term called as cos and theta is also here. So what to do about this? So what you can do is you can simply write it as real part of integral 0 to 2 pi. You can write this cos and theta as e की power iota and theta, because otherwise it will become very difficult, because z square plus 1 upon 2z raised to power n, that integration would be too difficult for you to do. So right away I would say that you should prefer doing this. So now this is, here you are having z square, this upon 3 plus z square plus 1 upon z, okay, and you have dz upon iota z. Okay, so this is how it is. So instead of the theta, you have written dz upon iota z and all sort of things. So here, why have conveniently used cos and theta as real part of e की power iota and theta? Because that will be too difficult. Because see, if you place n here, then you will have to expand it, and that will become very difficult. So I am doing it in this fashion. Okay, is that clear? Should I move ahead? भरत को समझ में आ रहा है, और कौन है? अल्पना को समझ में आ रहा है?
Sir, and there's the power of n also, no? First term में.
Okay, sorry, power n also. Power n. So, okay, is that clear? So
So
we can
ultimately हमें इंटीग्रल
ultimately
में
तो करना
power
ही
of n
पड़ेगा.
तो है.
कोई बात नहीं, चलो चलेगा. In any case we have to do it. So what would we do? कुछ कर नहीं सकते उसका तो. So we'll do z plus z square plus 1. अच्छा, वो पावर n वैसे भी यहाँ पे z की पावर n तो है ही ना. So I would what it will help me. This is how it is. Is that clear? And you have dz upon iota z. Is that clear to you? ये चीज समझ में आ रही है? And then you have something in division side, you have 3, I think, if I'm not wrong, z plus z square plus 1 divided by z. So you have z here. This z gets cancelled with this z, because ultimately this z would come on the numerator end. So this will get cancelled. This z raised power n gets cancelled. So so you can write 0 to pi. And then you have z square. Then you have z. Then you have plus 1 raised power n divided by, I think if I'm not wrong, I will write it in this way, z square plus 3z plus 1. Is that clear? And you have dz, and then you have 1 over iota. Okay, I already taught you in the very first, in initial classes of calculus of residues, that this particular integral is nothing but 2 pi iota into the sum of residues. Okay, this is equals to 2 pi iota into sum of residues, isn't it? So we have to find residues first. Okay, so let us first find residues. So what is first, in order to find residues, you should be in a position to tell and also understand that this integral, sorry, instead of writing 0 to pi, this integral is over a unit circle. Okay, since you've taken e की power iota theta as z, and theta varies from 0 to 2 pi, that implies what? That implies you are on the unit circle. You are on the unit circle traversing anti-clockwise. Okay, so you have to find the real part of integral 1 over iota. First find what are the residues. So that would be minus 3 plus minus root over 3 square is 9 minus 4ac is 4 divided by twice a. So a is 1. So z would be like z would be 1 minus 3 plus root over 5 upon 2. Another would be minus 3 minus root over 5 upon 2. So let us write it as alpha. Let us write it as beta. Beta will obviously lie beyond the unit circle. You can clearly see. That's fairly easy to see. But this will lie inside the unit circle. So z equals to alpha lies inside the unit circle. So you have to find the residue at z equals to alpha. So z tends to alpha z square plus z plus 1 raised power n divided by, I can write it as z minus alpha into z minus beta. And you can see that the coefficient of z square is 1. So I don't need to take anything common out, multiplied by z minus alpha. This is the residue of the function at simple poles. So simple, this gets cancelled. So you have alpha minus beta. So alpha minus beta turns out to be root over 5. Is that clear? Is that clear? I don't think there is an issue till now. So
Yes, sir. Yes.
eventually we'll get what? Eventually we'll get, I think, if I'm not wrong, eventually I will get this particular thing as 1 over root over 5, and then I will have some alpha square plus alpha plus 1 raised power n. So this is your residue of function at z equals to alpha. So this is your residue of the function at z equal to alpha. Is that clear? And what I have to do, I have to multiply it with 2 pi iota in order to get this integral. So this integral, and then I have to multiply with iota also, and then I have to find the real part. So what is the real part? Iota into 2 pi iota, iota gets cancelled with iota, 2 pi into this entire thing. This is real. So eventually, अच्छा मेरे को लिखना चाहिए क्या? Should I write this integral? So this integral will be, I'm writing it here. This will be 2 pi iota into this 1 over root over 5, and then alpha square plus alpha plus I raised power n. And the short integral that I'm finding is 1 over iota into this entire thing and this real part. So 1 upon iota into this thing. So iota gets cancelled, and real part, obviously this entire thing is real only. So there's nothing else to write. So your integral would become, I think your integral would become, if I'm not, it's like alpha square plus alpha plus 1 raised to power n, and then you have some, I think 2 pi. So 2 pi also comes here. So 2 pi upon root 5. So we have to find what is alpha square plus alpha plus 1. That we have to find. So that we'll find here. So alpha is what? I think root over 5 minus 3 upon 2, isn't it? So what will be alpha square? Alpha square would be 5 plus 9 minus 2 root over, I think 6 root over 5 upon 4. And then you have some 1 also. So you have to add all these three terms. So you just make it 4, you just multiply it with 6, you write to alpha square. So you just add all these three terms. So adding all these three terms would give you 2 root over 5 minus 6 plus 14 minus 6 root over 5 plus 4 upon 4. Okay, so this is it. So eventually you are left with 4 plus 14. 14 is 18. 18 minus 12. And this 6 minus, I think this will be minus. Some negative term also is coming out. Sorry, positive रहेगा ये तो. So this will be positive, I think, because 4, 18, 12. ठीक है? Or this will be minus and this will be
3
so
minus root 5.
So 3 minus root 5. So answer is 3 minus root over 5 raised power n. Okay. And then you have division by root 5, and then you have 2. So this is your integral. Is that clear? अल्पना को समझ में आया? ऊपर से चला गया है? अल्पना है भी क्लास में?
हाँ भैया आ गया.
ठीक है, तो ऐसे करते हैं. ओके. देखो, next category of integration that we were doing, and probably you were absent in that class, that were oscillator integrals. That were integrals of this type, minus infinite to infinite fx dx. So such integrals can be found using, instead of this evaluating this integral, we will evaluate this integral over a contour C or gamma, whatever you wish like saying. And that contour is a semicircular contour. This we have already done. And we have proved that. I will also prove again, I will give you a proof again, that while I integrate over this semicircular arc, which I am representing by this gamma, it will turn out that this integral over gamma is 0. So what I want to say is, if I want to evaluate this integral, I would say just forget about this integral. Evaluate this integral. This particular real integral, I'm saying just replace it by this contour integration. Why? I'm saying it because if I want to find this contour integration, this will be equals to minus R2R plus integration over this gamma. What I'm saying that as R tends to infinite, this particular integral would obviously go to 0. This is what we've done in last two classes. This integral would go to 0 as R tends to infinite. And you are left with minus infinite to infinite. And here you have fz dz. And since you are writing fz dz and you are on the real axis, either you write x, either you write z, one and the same thing. So basically minus infinite to infinite fx dx integration is equal to this kind of integration. So this is the beauty of putting this into picture. I mean, this makes our life a little bit easy. Is that clear? यहाँ तक समझ में आया? I will do a question from this also and we'll move ahead. Okay. Okay. So let us do a simple question about it. मतलब इसके ऊपर एक question करते हैं. Let us do a question. So a question would be, I think, let us do an integral from 0 to infinite. And here you have dx upon 1 plus x square whole square. So clearly you can see this is an integration. So for example, if you had 1 plus x, however, if you tell me I can do this integration using definite integrals, what we have studied in standard 12th. But for you people, it will be difficult for do. So what I would do is I would prefer doing it from complex integration, okay, using complex integration. So how would I do that? So here it is. So here I'll be doing something like this. Okay. So this integral I is equal to 0 to infinite dx upon 1 plus x square raised power 2. And how to go about this particular integration? So what I would do is I would simply, okay. So first thing, understand, I would replace it by a contour integration. So instead of this, I will say, forget about it. Just make a contour. And that contour is a semicircular contour. Okay. And I've told you for all purposes right now, I'm taking upper half. I will do a lower half also one day so that you will be able to understand. So this is my contour. This is my, let's say, gamma. अब ध्यान से देखना. So this particular integration I can replace by minus r to r 1 integration plus integration over the semicircular arc. Okay. Now let us evaluate this integration at first. So what would it be? So this would be dz upon 1 plus z square whole square. Okay. So let us evaluate what sort of integration, what sort of value it would take as r tends to infinite. Because in order to evaluate this integration, अच्छा एक और काम करो. This integration can be modified by 1 over half minus infinite to infinite dx upon 1 plus x square की power 2. And this is the integration which I'm interested in. And this integration I'll find using contour integration. I told you, replace this integration by this. So I've replaced this integration by this. And whatever the value for this integration comes out, just multiply 1 over 2 and you will get the value of this integration. Is that clear? कल्पना यहाँ तक समझ में आ रहा है कि ऊपर से जा रहा है?
हाँ.
Okay.
यहाँ
So
तक तो आ रहा है.
what I would do is I would try to find the absolute value of this integral. Absolute value of this integral would be, I would write this way, I would write this way, and this is how I'm going to write. Okay, is that clear? Okay, is that clear? So ek kaam karo, what I would do is I would say that instead of, I will write here that what I would do is 1 plus z square ka mod. So for example, I'll write something here. So for example, if I write some complex number ka square ka mod, or if I write mod of complex number ka square, they mean one and the same thing. See why? So for example, I'm writing एक मिनट इधर देखते हैं पहले लेफ्ट, इसको थोड़ा ध्यान से देखो. लेफ्ट हैंड साइड को देखो. लेफ्ट हैंड साइड क्या है? एक्स स्क्वायर माइनस वाई स्क्वायर कॉमा 2xy का मॉड लेना, एंड विच इज इक्वल टू रूट ओवर, है ना, रूट ओवर एक्स स्क्वायर माइनस वाई स्क्वायर का स्क्वायर करना एंड देन 4x square y square. Is that clear? Z square का mod ये तो होगा. And if you just open this bracket, this will be x raised power 4 y raised power 4 minus 2x square y square plus 4x square plus y square. So this is 2x square y square का root over. And overall you will get x square plus y square ka whole square, and root over is x square plus y square. And what is x square plus y square? It is nothing but it is equal to mod z whole square. Is that clear? Yearly property समझ में, and same applies to any sort of exponent. So this is a property complex analysis. So what I would do is, instead of writing 1 plus z square, I will say So this is one mod. Okay, understand my point that Z1 plus Z2 का जो mod होता है, it is always greater than equal to difference of this two complex. Is that clear? This is what is called as triangles inequality. So this is what is called as triangles inequality. You can take it in this fashion: sum of two sides of triangle, difference of two sides of the triangle. Okay, so this is triangles inequality. So what I would do is, instead of okay, and further if I do, for example, instead of adding these two complex number, if I add modulus of these complex number, so obviously this will be greater than this, and this will be greater than this. Is that clear? So if I write 1 plus z square ka mod, so 1 plus z square ka mod will be greater than equal to 1 minus z square का mod. Is that clear? ये चीज इन दोनों को देखो, z1 की जगह हमने लिख दिया 1 और z2 की जगह लिख दिया हमने z square. Okay, so effectively what I will get is, effectively I will get something like this way. And if I write 1 plus z square का mod, it will be less than equal to 1 upon 1 minus mod z का whole square का mod. And if I take a square over it, so it will be this way. Now understand my point that mod z is r. Clearly see that on this integral, on this particular semicircular contour, your z can be represented by, your any point z can be represented by r e to the power iota theta. Okay, so if I represent that entire thing as r e to the power iota theta, where theta lies from 0 to pi, so mod z will become r square. So eventually I will write that this part, kind of integral 1 plus z square का mod का whole square is less than equal to 1 upon 1 minus of r square का whole square. Is that clear to you? ये चीज समझ में आई? So what I can do is, this particular integration that I'm like encircling right now, this I'm saying right now, what it is, it says 1 plus z square का whole square का mod का mod. So what I can do, I'm writing it here. So this will be equals to integration dz का mod over this gamma divided by 1 plus z square का mod का whole square. I told you that anything square का mod or mod का square is one and the same thing. And I already told you 1 plus z square का mod का square is less than equal to ये जो लिखा हुआ है, so I'll write it as 1 minus of r square का whole square. And what these remaining term will be what? Integration dz का mod. What is dz का mod? Dz is just the length element. And all these length element when added on the semicircular arc would give you the length of the arc. So what is the length of the arc? This is pi into r divided by 1 minus r square raised to r whole square. So eventually what you see is that as r tends to infinite, limit, as r tends to infinite, this is r square ka square. So power in the denominator is greater than the power in the numerator. Overall, this term will tend to 0 as r tends to infinity. And you'll find that this integration ka jo modulus tha, this is what it was. So this was what? This was integration fz dz ka mod. So integration fz dz ka mod was less than this. And if I take, okay, so this is less than this and this is less than 0. And understand, anything's modulus cannot be less than 0. Okay, negative nahi ho sakta. It has to be equal to 0. So what you will find is this integration is 0. This integration is 0 as r tends to infinity. Is that clear? ये चीज समझ में आई, ऊपर से चली गई?
सर एक बार फिर से
हाँ।
बताना मुझे।
वापस बताऊं?
बहुत लंबा।
ठीक है, so what I would do is,
रेड पार्ट वाला है तो।
एक बार वापस सुन लो. देखो जो फंक्शन का जो ये वाला, देखो इस कॉन्टोर इंटीग्रेशन को मैं दो पार्ट्स में तोड़ रहा हूँ. एक तो जो एक्स एक्सिस पे चल रहा है और एक ये सेमीसर्कुलर आर्क पे जो चल रहा है. इज दैट क्लियर? अभी जो सेमीसर्कुलर आर्क पे जो चल रहा है, इसका मॉडुलस मैं कह रहा हूँ, देखो ये दिस मॉडुलस, दिस विल बी दिस मॉडुलस. समझ लो, dz अपॉन 1 प्लस z स्क्वायर का होल स्क्वायर ओवर दिस सेमीसर्कुलर आर्क का मॉडुलस. सॉरी, आई शुड नॉट राइट इट एज less than equal to, and this will be less than equal to integration अंदर. ये याद रखो, ये property. So this is a property that integration fz dz का mod is less than equal to integration fz का mod dz. ठीक है, ये चीज तो याद कर लो अभी के लिए, because there are too many things then to do. Okay, so what I have done, I have done this. Understand that I have used a property that is z1 plus z2 का mod is greater than equal to mod of z1 minus mod of z2 का mod. Okay, and इसको याद रखने का तरीका क्या? Sum of two sides of a triangle is always greater than the third side यहाँ पे नहीं है, या the difference of two sides of a triangle है. So basically ये सब complex numbers में आता है. So initial like standard 12th में अगर तुम जाओगे तो you'll find all these kind of things written in your books. Okay. So now what I would do is I would say that 1 plus z square. So instead of z2 I have written z square. Instead of z1 I have written 1. So 1 plus z square ka mod will be greater than 1 minus mod z ka mod of z square. And I've taught you that z square ka mod lena ya mod z ka square lena baat ek hai. Understand that on this particular semicircular arc, your mod z is r. Mod z is simply r. So this will become r square. Is that clear?
Yes, sir.
ठीक है. So 1 upon 1 plus z square का whole square will be less than equal to 1 upon 1 minus r square का whole square. देखो इसको डिवाइड करो तो ये इनइक्वालिटी उल्टी हो जाएगी, and then take square both sides. Is that clear? So you'll find that 1 plus z square का mod का square will be less than equal to 1 minus r square का whole square. Is that clear? ये चीज समझ में आई? अब ध्यान से देखते हैं this integration, that is mod of integration fz dz over semicircular arc in the limit r tends to infinity is less than equal to limit r tends to infinity. ये वाला जो mod है अंदर लेके गए थे, याद करो. और अब देखो ये 1 प्लस जेड स्क्वायर के मॉड का स्क्वायर जो है वो खुद किससे छोटा है, 1 माइनस आर स्क्वायर की पावर 2 से. सो आई विल राइट लेस देन इक्वल टू 1 माइनस आर स्क्वायर की होल पावर 2. ये तो कांस्टेंट है, इसको बाहर ले लो. अंदर क्या रहेगा, इंटीग्रेशन मॉड डीजेड. इंटीग्रेशन मॉड डीजेड रहेगा सिर्फ अंदर. इंटीग्रेशन मॉड डीजेड का मतलब क्या हुआ, ओवर गामा. तो ये समझो ये जो गामा था इसके ऊपर डीजेड का मतलब क्या होता है, सिंपली ये छोटे 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 एलिमेंट्स ही तो है. इन सारे छोटे एलिमेंट्स के डिफरेंशियल डीजेड्स को अगर तुम ऐड कर दोगे तो क्या मिल जाएगा तुम्हें, लेंथ ऑफ नहीं मिल जाएगी, लेंथ ऑफ दिस पर्टिकुलर सेमीसर्कुलर आर्क. देखो अगर मैं कहता हूँ ये तुम्हारा कोई लाइन है और आई एम सेइंग कि dx 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 सारे ऐड कर दो, तुम नहीं कहोगे कि यार इट इज इक्वल्स टू व्हाट, इट इज इक्वल्स टू x2 माइनस x1. इजंट इट? जैसे dx का इंटीग्रेशन करने को कहता हूँ तो यही तो हुआ. ये तो क्योंकि पॉजिटिव साइड में ही था तो यहाँ मॉड वॉड लेने की कोई जरूरत नहीं थी. लेकिन यहाँ मॉड का मतलब क्या है, dz का मॉड मतलब लेंथ ऑफ डिफरेंशियल एलिमेंट, और लेंथ ऑफ ऑल दीज डिफरेंशियल एलिमेंट व्हेन एडेड वुड गिव यू द पाई इनटू r. सो दिस एंटायर मॉड integral, I will write again this thing ka mod, which is your second integral ka mod is less than equal to 0. Understand, anything mod cannot be less than 0. Mod का मतलब क्या होता है, positive. So it cannot be less than 0. It has to be what, equal to 0. Since it has to be equal to 0, what will happen, this integral will become 0. So this is your integral I2. I will write this integral will become 0. Is that clear? अभी समझ में आया कि अभी भी नहीं समझ में आया?
यस सर, आया सर. मॉड हमारा आया कहाँ से वैसे, एक बार बताना. स्टार्टिंग में ही मतलब जो हमने
स्टार्टिंग मॉड
इंटीग्रल्स
नहीं
को
था.
डिवाइड किया
नहीं नहीं नहीं, मॉड
उसमें
नहीं था.
मॉड इंटू.
मैंने जानबूझ के मॉड लिया. आई हैव टेकन मॉड ऑफ दिस. ठीक है, आई वाज इंटरेस्टेड इन फाइंडिंग व्हाट वुड बी द एब्सोल्यूट वैल्यू ऑफ दिस फंक्शन, सो आई हैव टेकन अ मॉड हियर deliberately.
ओके ओके.
Okay, so these are all mathematic trick, you can say tricks on
ओके.
maneuvering, because whenever we have to find a absolute value of function to be 0, so what I do, I will take this. So this is pretty norm in mathematics. I would give you a theorem also now. Okay, so you don't. So eventually, yesterday also I told you that whenever you have to find this integration, forget about this. This integration would any day come out as 0 only, provided your function का mod should tend to 0 as mod z tends to infinity. कल लिखवाया था, याद करो, है ना? So
Yes.
again नहीं, मैं वापस लिखा दूंगा. ठीक है. So ultimately understand this integration over an arc will be 0. So you're left with this minus r to r only. And as r tends to infinity, this will become minus infinity to infinity. So your left hand side is there intact. I'm not disturbing that. So I'll write it all over again. See here. So your left hand side is dz upon 1 plus z square का whole square over contour C. This contour C is nothing but a semicircular contour from minus r to plus r. Then this is gamma, this is this. And you're left with two integration minus r to r. And then you have gamma. Now, as r tends to infinite, this particular integration has gone to 0. And you're left with only this integration. On the right-hand side, you have this integration. That is, right-hand side integration I'm writing here, minus infinite to infinite dx upon 1 plus x square ka whole square. Because whether you write fz dz or you write fx dx, they mean one and the same thing on the x-axis. Because on the x-axis, your y coordinate is 0. So you're left with x coordinate only. Is that clear? So here, this particular thing is on the right hand side, and this is equated to what? This is equated to this dz upon 1 plus z square. Understand my point that this particular thing, ka whole square, sorry, what sort of singularities lie inside this C? Because even as r tends to infinite, only one singularity lies, that because singularity kya hongi iski? Z equal to plus minus iota.
Plus iota, yes.
Only iota lies inside. Minus iota to niche रह गया, भूल जाओ उसको. Okay, so only on the upper half of the semicircle you have iota, and you cannot argue कि यार ये तो छोटा semicircle ले ले तो ऊपर तो क्या होता है. I'm already saying r tends to infinite. That implies you are taking as large as possible a semicircle over upper half of the plane. So eventually this particular thing would be equals to what? This will be equals to 2 pi iota into sum of residues. And what you have to do, you have to just find residue as z tends to iota. Understand that z equals to iota is a double pole here. Okay, so double pole के लिए क्या करना पड़ता है? 1 upon 2 factorial. क्या करता है? 1 upon m minus 1 factorial, right? So 1 upon 1 factorial d upon dz z minus iota का square into 1 upon z minus iota into z plus iota. ये हो जाएगा 1 plus z square का whole square. Is that clear? This will get cancelled. Okay, and all of these things you have to find at z equals to iota. Is that clear? So what you're left with 1 upon 2 iota का whole square, if I'm not wrong. ये फॉर्मूला तो सही लगा ना, d by dz of z minus iota का square. I think 1 upon n minus 1 factorial होता था, 1 upon m factorial होता था. Just check
n
it.
minus 1.
n minus 1 होता है.
ठीक है, so 1 upon 2 minus 1 ही आएगा यहाँ पे. So I think this will be equals to minus 1 over 4, if I'm not. Iota का square तो ये रह गया. I think this is it.
आपने वो स्क्वायर वो d by dz है ना, वो तो उसका
अरे
स्क्वायर
हाँ
नीचे वाले से
हाँ,
काट
I'm so sorry. मैं सोच रहा हूँ क्या गलती हो रही है. ठीक है, so एक मिनट रुक जाओ. I'm so sorry, this is wrong. ठीक है, so I have to differentiate also, no? I have to differentiate it also. Sorry. So differentiate करेंगे तो d by dz of this would give you what? It will give you, अरे यार, ठीक है, it would give you minus 2 upon z plus iota का whole cube. Is that clear? And then you have to take z equals to iota. So now if you take z equals to iota, what you will get? You'll simply get minus 2 upon 2 iota का whole cube. So this is minus 2 upon 8. Iota का cube is minus iota. So this will become, I think, 1 upon 4 iota. Okay, so 1 upon 4 iota is the residue. You have to take into multiplication 2 pi also. So officially this integral on the left hand side is 2 pi into 1 upon 4 iota into iota. So overall this integration is pi upon 2. So your left hand side pi upon 2 is equals to right hand side, which is minus infinite to infinite dx upon 1 plus x square ka whole square. And what was asked in the question? Question asked was 0 to infinite dx upon 1 plus x square ka whole square. This is equals to half of it. So answer would be equals to what? Pi over 4. Is that clear? So it was very difficult integration when it comes to standard 12 techniques, but like now you can do it in an easier fashion. Is that clear? बढ़े आगे? Okay, now let us move to something called as Fresnel integrals. Okay, Fresnel integrals. Okay, so they'll be used mostly in optics and diffraction, but overall here our motivation is to find an integration to this. Okay, so if I'm telling you to find integration to this, let's say this sort of integration, or probably this kind of integration 0 to infinite cos of x square dx, how would you go about these integration? इस तरह के integration को कैसे evaluate करें? Let us see. So what would you do in these integration? This is slightly special integration, that is why I'm doing it for you. So what I would do is I would use a symmetry. And understand that in such integrals, the choice of contour is very important. The choice of Otherwise, this will become very difficult. Choice of contour is supremely important. Okay. So what I would do is I would take a contour in such a manner that things become easy for me. Okay, things becomes easy for me. And what I would do, now this is an integral where what we do is we choose an integration, we choose a contour as an arc. So till now you've seen semicircle and all those things. Now, so certain integrals you have to remember. So you take an arc over here. So you take an arc, and that arc, like let's say if I write it as U O, or probably I'll write B here. Okay, so I'll take an arc called as UAB, and this is tilted at an angle pi by 4. Understand, pi by 4 is that angle where your sine and cosine become equal. Okay. Okay. So now, so instead of semicircle contour, I'm taking this contour. Okay. And don't say why I'll be taking this is an elaborate mathematics. People have done all sort of thing, and eventually they ended up choosing this contour for this particular problem. Okay. Now, how to go about it? So what I would do, instead of doing this integration, I would do this integration. E to the power minus z square dz over c, where c is this. Your c is this. So effectively, I'll write this as integration OA, integration over AC, and then integration over BO. Okay, and this is an arc AC. This is OA is a straight line, and BO. Okay, so what you can do is probably another class also would come. We'll have to see that. So OA, along OA, understand, if I go along OA, so OA is nothing but it is equals to x-axis. So your z becomes equals to x. So it is equals to writing e to the power iota x square dx. Is that clear? Along arc BO, what sort of points will lie? See, for example, if I rotate now, any point on this complex in this particular line can be represented by the radial distance r and the angle, that is pi by 4. Is that clear? If I write in polar coordinates, so any point on this line can be written as r comma theta. Theta would be pi by 4. R is the radial distance from the origin. Is that clear? So any point
Yes.
on line BO can be written as r e to the power iota pi by 4. Is that clear? And this r varies from r to 0, not from 0 to r to 0. See. Okay. So this integration, I would prefer to write r to 0 e to the power, I think I will have to write e to the power iota. Z square is r square e to the power iota pi upon 2. And then I will have some, I will write dz here. So dz will be e to the power iota pi by 4. And variable here is r. So this will become e to the power iota pi by 4 dr. Is that clear? I'm not wrong. Am I doing something wrong here? No, I don't think there's something wrong. There's something wrong, not here. Okay. Now, what
pi by
about this?
2 कैसे आया sir?
You take a square. So taking a square would give you.
Okay.
Okay. So overall, I think this AC, this integration AC, we'll have to see. And understand my point. We are integrating from 0 to infinity. So we'll take eventually r tends to infinity. At the end, we'll have to take r tends to infinity. Let us first find how does this AC behave? How does this AC behave as r tends to infinity first? So what is AC? So along arc AC, your point, your I think I'll write it here again, show you here, and I'll end the class right now after this, and we'll continue it in the next session. Okay. So on this arc AC, probably not AC. What is that? AB. Oh, sorry, AB. Along the arc AB, what I can say is my points can be written as r e to the power iota theta, isn't it? Okay, I forgot to mention here. Okay, so my points on the arc AC can be written as r e to the power iota theta. Is that clear?
Yes.
And your theta varies from 0 to pi by 2. Your theta varies from 0 to pi by 4. Sorry, 0 to pi by 4. Is that clear?
Yes, sir.
Okay, so we'll take it in the next class. Okay. So theta varies from 0 to pi by 4 to this, and your r is a constant here. Okay, so we'll take it in the next class.